Welcome everyone for Raychaudhuri equation part 4. So let's summarize what we studied last time. This is the Einstein's field equations. Right hand side gives the mass, mass of these planets or whatever in the region. Left hand side gives the curvature. Except this term that is called the cosmological constant that would be valid for large scale distance, the size of the universe. If you are considering the whole universe, then this term would be valid. Otherwise, we could ignore this term. And these two R terms, one is the Ricci tensor and the other one is the Ricci scalar. These two terms gives the curvature of the space-time. So this side gives the mass. So the mass, if you change the mass, curvature changes. Now, what did Carlschwarzschild did? So that's what we are going to find out in this lecture. Before we go there, let's look at an analogy. So this is the analogy I'm going to take. So let's look at an analogy. Before we go there, let me talk a little bit about Carl-Schwarzschild. So Carl-Schwarzschild found a solution to Einstein's field equation just only 1 month after Einstein published his field equation. That's an amazing feat. Just to understand this theory and come up with a solution to field equations was remarkable feat. And not only that, he was a soldier in the First World War fighting, and he was in the battlefield, and when he was free he just did some work and came up with the solution. That's an amazing story. So now let's go back to the analogy here. Let's say there's an hexagon here. Now we need to find the area of the hexagon. So the whole world is looking for an equation for this hexagon, and then someone comes up with this equation. But there's a problem. You need to find t, the length of one side. So how to find t? So people are stuck again. To find t, let's say this hexagon is inside a room, let's assume. So to find t, you need a ruler. Someone says, aha, I know, I have a ruler. We just make a ruler here. So that's exactly what Carl-Schwarzschild did. He found a ruler to measure Einstein's field equations. So he came up with something called Schwarzschild metric. Schwarzschild metric to solve the Einstein's field equations equals ruler to measure the length of a side in our analogy. So now this is the Carl-Schwarzschild metric. ds squared, s is the distance between 2 points. ds squared, ds is the small distance. ds squared is the square of the distance. But if you look at the right hand side, rs is the Schwarzschild radius, which we are going to talk a lot later, has an m term in here. So our ruler is dependent upon the mass. So it's like going back to here. Let's say we have this hexagon inside a room, and someone found a ruler to measure it. All good. And then suddenly someone brings a table into the room, and then the ruler changes. Now ruler, it's a 1 foot ruler, now suddenly it's something else because the mass of the room has changed. I'm using an analogy. That's exactly what happened here. So this is ds squared, and all this is Schwarzschild metric, but the metric has a mass term. So because of that, if you change the mass, ruler changes, Schwarzschild metric changes. Now you could use this metric and apply that matrix comes as G. So once you know G, you could solve gamma. I mean, I'm just saying, in a very easy manner. Like if you ask me how to be the president of USA, all what you have to say is you become a senator or congressman, and then become, have national recognition, and then you run for White House, for presidential election, and then you win the election and you be the president. It's not easy as it sounds, but I'm going to make it something very simple statements here. So once you have the metric, that would be G, and then you could find gamma. And once you have gamma, you have here, and then these are all coordinate terms, and then you could find the acceleration. So for any given metric, you could find the acceleration. And this is the geodesic equation which we did last time. Now, if you go here, there are some problems with Schwarzschild radius, which is we are going to talk in our next lecture. Now, what's going to happen when r equals 0 at the center, and this term goes to infinity? So that's why we say Einstein's field equations are not valid at r equals 0, because this is undefinable. And what happens when r equals rs? R equals rs, and this term goes to 0, and this term goes to infinity. So r equals rs and r equals 0 are two big problems for Einstein's field equations. And that's the subject of the next lecture. Thanks for listening.